here. If she doesn't want to say hi, it's okay. All right, so the idea.
Sorry, I sound so bad. But I'm watching.
Oh, Nina, we miss you. All right, so the idea here is that each of these terms, the way they're being constructed, controls one of the derivatives of our polynomial. So while I would like to compare this with a tangent line shared a point and a slope. Taylor polynomials are going to kind of answer the question, well, what if we wanted to match the second derivative and the third derivative and the fourth derivative? Eventually with Taylor series, what if we match all of the derivatives? Can we get a function that's a polynomial that's equal to our function? Rashad?
Are we bringing back like extra on like the first derivative?
No, so we won't be bringing back that stuff because these are actually really hard to construct. So we're going to focus mostly on how to construct a polynomial that would either approximate or eventually equal our function. So let's talk a little bit about this formula. I'm going to kind of reference back really quick to a couple of the reasons why some of the things are here, but we need some verbiage first. So back when we were doing tangent lines, we might have talked about the x value where we wrote our tangent line as like the point of tangency. That was like the x value that I plugged in to find my y value, to find my slope. That has a new name for this. So all of these C's, I'm just going to point at one of them, but it's all of the C's. This stands for center. So in the example you saw in the video, that center would have been 0. That's where they're plugging in to find all their derivatives. That's where they're plugging in to find that y value. That's going to be a very, very important thing to know whenever we try to find our Taylor series. Now, you may be noticing that there's two formulas that are very, very similar. What's the difference between this guy right here and this guy down here? All right, what does it look like the center is? 0. And all of these x minus c's are just x minus 0, so they look simpler. The different name for that is a Maclaurin series. So Taylor is an English mathematician. His name's Brooke Taylor. Maclaurin, I think, is a Scottish guy. So I like the story in my head. I don't think it's actually true, but the story in my head is that Maclaurin saw Taylor series and he was like, I'm going to set her that at 0 and name it after myself. Really, all you need to know is that if I ask for a Maclaurin series, that's me saying a very fancy way to tell you the center is 0. So that's literally the only difference. Wow, that is not how you write the word center.
So it's a special name.
Yep, it's just a special name and just a coded way for me to tell you the center is 0. We're going to eventually memorize about 4 or 5 different Maclaurin series in general so that we can build off of them. And we're going to kind of use this formula today to build some of ours. Now, a couple of reasons the way this series is constructed the way it is. You notice that when we were taking derivatives of the cosine one in the video, everything kind of matched up really well because when I plugged in 0 to the x's, it kind of made all of the rest of the terms go away. That's why this x minus the center is here. That's helping us make sure that each one of these terms only controls its specific derivative. Can anyone think of why the factorials are there? All right. I'm going to try to scroll through here in a second. Where is that place? As you go through and start taking derivatives, notice here to match up the stuff that you want, you kind of have to divide by whatever derivative you're at. So if I'm looking at the fourth derivative, I would have had to take 4x cubed, 3x squared, 2x, and down to 1. So this, to get rid of that stuff as I'm taking derivatives, that's why we're going to end up dividing by n factorial. It's not super important that you know why. It is in this video if you want a better explanation, but that process of like matching up the derivatives, that's where that factorial is coming from. So why the 1/2 was there, the negative 1/2 in the cosine one. As we move further, we're going to need more and more derivatives. So that's why that is there. So let's talk examples. The other thing that you may want to know, sometimes a lot of AP questions ask specifically about the coefficient of any given term instead of making you write the full Taylor polynomial. So our nth derivative over n factorial is a quick way to find any given term's coefficient. So that may get asked about, just a factoid there. So again, we're going to practice using this formula today. If you want further explanation of why the formula is the way it is, I certainly can give it to you. I have it all prepped. But for right now, let's just focus on using it. I'm going to show you some graphical stuff that'll also help justify why we're doing what we're doing. So the first one, literally just going to practice plugging into the formula and kind of deciphering what a question might be. So this one I'm not going to be able to graph to show you because f is just a random function out in the ether that we don't know about. But we know 4 very specific values that relate to f or its derivatives. Notice that the question is pretty straightforward. They're asking us for a Taylor polynomial of degree 3. What do you think that means, of degree 3? All right, we're eventually going to need the third derivative because the degree is going to be whatever this biggest power is. So that nth degree, our biggest power is going to be that degree. So we're going to end with the x cubed term. All right, so I will need 3 derivatives. Looky there, the thing I have is f triple prime. All right, we are also centered at x equals 2, which means I'm going to see a lot of x minus 2's in my Taylor polynomial. I also need all of these derivatives at 2. Last piece of information, a lot of the times these get labeled P sub 3 or capital T sub 3 for Taylor or polynomial. The sub 3 is telling me what that degree is. So just if you see that notation, that's what they're talking about. So to construct this, again, we're really just going to be plugging into this idea of a formula. We'll talk a little bit as we go. So the first term in our Taylor polynomial is just going to be that y value, so that 3. That's ensuring that the y value of this polynomial is equaling the y value of the function f. The next term, anyone think they know what it's going to look like? -4, and on the back end of that is going to be x minus 2. So x minus our center. Now, if we stopped here, this is actually a tangent line. If I moved this 3 over, doesn't that look like a tangent line? So you actually have been doing first degree Taylor polynomials already since AB calculus. Wow, how brilliant.
How brilliant.
Yeah.
If the center was at 0, you would just write an x after.
Perfect. Exactly. So that's why we kind of like Maclaurin. It's probably why it deserves its own name, is because a lot of the time those are much easier to deal with. All right. Then once we get to our second degree term, things start getting a little spicier because we have to start with our factorials. I don't know why I wrote the number 5. What number should I be writing? 7 over 2 factorial. Now I know 2 factorial is the number 2. You could write either one. Generally, these though are not going to be really simplified ever. Our job is usually to create a Taylor polynomial. So not only am I usually going to leave the factorials as they are, but one thing we will never do is like multiply all of this stuff out. We're going to keep the x minus 2's preserved because we want to know where this thing was centered. All right. Last term, anyone want to take a stab at it? Beautiful. All right, so this is our Taylor polynomial of degree 3 because we're ending with our third power, centered at 2 because we see all of those x minus 2's. Again, we're not really going to simplify. The most you would probably see is that 2 factorial is 2, that 3 factorial is 6 from 3 times 2 times 1, but we're never going to multiply out because we want to see those x minus 2's. All right, the last thing we're going to do to answer this question is it actually asked us 2 questions. It asked us for the, I spelled that wrong. No, I didn't. Coefficient. All right, what would you call the coefficient of the third degree term? -5 over 3 factorial or -5 over 6. So just kind of reiterating that coefficient means the number in front of that term, not the whole term itself. So we would just want the number. Yeah.
Where did you get the -4?
Given as my first derivative. So I could write this over 1 factorial if I wanted to, but that's going to be my first derivative there. So the nice part as you go to memorize this formula, because I will not give you this on a quiz or a test, is the nice part is kind of our number of our derivative, our degree on the x minus the center, and the factorial all match with each other. So the terms are relatively similar. Ashley.
Do we For like the coefficient, do we have to?
Nope. I just did if you wanted to. All right, so you may be asking, how does this get hard? Because this doesn't seem very hard. What if we have to find the derivatives ourselves? Yeah, and the point of this, I already agree with your groans, because right here, I'm going to be asked to find the fourth degree Taylor. So how many derivatives do I need to find? 4. That's obnoxious. So we're going to spend pretty much the rest of this unit finding better ways to find Taylor polynomials. Matt.
So I see keep on taking derivatives.
Yeah.
Just keep putting it apart.
Good question. There is a better way. Because I agree, quadruple prime starts to get a little annoying. So let's talk about this. And as you guys take these derivatives, I'm gonna try to get a graph up so we can kind of see what this is doing graphically. So here, you guys are right that we need 4 derivatives, but Matt's question is a really good one. After triple prime, we get tired of doing primes. There is no F quadruple prime. Super brownie bonus points. Does anyone remember what the notation is for derivatives after this point? You put some parentheses and a number. So that 4th degree is there. You could probably see that up in this guy, the nth derivative right here. See if you put parentheses around that. All right. Anything you guys want to tell me about taking these derivatives? Because I'm going to have you guys do it. Chain rule. Wow, what a great idea. So e to the 3x, I'm going to chain rule. My first derivative would be e to the 3x times 3. All right, you guys are going to find all of those derivatives, and then I want you to plug in the center. Anyone see what the center is? 2. So you're going to plug in 2 to all of these. I want you to leave them in terms of e. So you're going to have e's in all of your derivatives and all of the things you're plugging in. I'm going to start a graph up. If you're feeling really fast at this, feel free to go and start writing your 4th degree Taylor polynomial. It's going to take me a second because this graph is kind of enormous. All right, and I need what is it? Oh, it's 3x. Sugar. How big is that? 400. Mm-hmm. 'All right, you guys got my derivatives ready yet?
Yeah.
All right. Anyone want to tell me what my second derivative is? All right. Third. Last one. You guys are so good at multiplying by 3. All right. What's going to happen when I plug in these 2's? Perfect. I'm going to have a 6 in my parentheses, or in my exponent parentheses. All right, now, why did I choose an obnoxious function like this where these guys all have e to the 6 in it? Mostly I wanted to show you that these don't have to be nice numbers. A lot of the time they will be kind of integers like we were working with here, but they don't have to be. So what we're going to do now is we're going to write this Taylor polynomial term by term. After every term, I'm going to go back to the graph and kind of try to do what that video was doing for you and show you what this is matching as far as the graph. So we're going to flip back and forth just to kind of get a visual of what's happening. So I'm going to write my 4th degree Taylor. What will the first term of that Taylor series be? E to the 6th. So looking at this graph right here, if I just put in e to the 6th, notice all I am matching on that graph is just the y value. That's not doing a very good job of approximating anywhere but my center. I get pretty far off pretty fast because look at the scale of this y-axis right here. We're going from 0 up to 2,000 because this graph grows pretty fast. So let's see how accurate we can get as we start adding on terms. Anyone want to tell me what the next term is going to look like? All right, 3e to the 6th, x minus 2. You can, if you want to be super consistent, do like a 1 factorial and a 1. Technically, 0 factorial is also 1 by definition, if you want to throw a 0 factorial on there as well. All right, so I'm going to do plus 3e to the 6th, x minus 2. So notice here, we're at effectively the tangent line stage. We have matched the y value and the first derivative. We're doing a much better job approximating a little bit farther from that point, but there is still room to be desired for accuracy. Once we get out a little bit farther than maybe, I don't know, 0.1, 0.2 away, we're not doing that great of a job. All right. Next term. I don't think Mr. Corker wants to do math.
9e to the 6th over 2 factorial.
Ooh, 9e to the 6th over 2 factorial. X minus 2 squared. All right, it's going to take me a second to type that in, but as I do, remember this picture. I want you to see how much more accurate does this get. And Desmos, you can do 2 factorial, which is pretty, sorry. X minus 2 squared, and let me get rid of that parentheses that's at the front. All right, so looks a little bit better. That was a little bit of a forced well, but I'll take it. I'll take it. Yes, ma'am.
If you keep adding like more,
yes. So as I add more and more derivatives, the better my approximation gets. So as we kind of talk about this, we'll have to figure out how far do we want to go. Yeah. Yes. So the point of this is I'm kind of finding a specific answer here. So they're asking me for a specific number of terms here. Eventually, we'll have some patterns that we can go on. All right, let's get these next 2 terms. Will you just tell them to me? I'm going to type them in to save us a little bit of time. What's the next term going to look like? I'm just, yeah, that's pretty much what I hear. So I'm just assuming that I hear what's right. All right, here, we're getting even better. That right-hand side, it almost looks like it matches that graph. I know my scale is a little bit huge, but we're getting a really, really good approximation. This last one, I'm guessing it's 81e to the 6th, all over what? 4 factorial. Cool. So notice that right-hand side, we are doing a real good job on that right-hand side. Now, this left-hand side is kind of wiggling back and forth because we have a polynomial. So we're only going to get so good at this right-hand side. But with this dot right here is our center, or close to it, I guess. So these are doing a really, really good job close to the center. Yes, ma'am. Oh, yeah. Sometimes it's going to be easier to see than others. There's definitely going to be some patterns. Absolutely. This function tends to be pretty easy to work with because of the derivatives of e are easy to figure out. We'll have other functions where the derivatives aren't kind of as predictable. All right. So let me finish writing this. Can you guys tell me, did we answer the entire question? All right. The coefficient of which term? Oh, so the one I'm writing right now. 6. All right, so my coefficient is 81e to the 6th all over 4 factorial. All right, so as we finish up that question, would you agree that that was an annoying process? All right, so ideally, I don't want to have to take 4 derivatives to be able to do this. So eventually, we're going to get a lot of tools that will help us build this without taking those derivatives. Because I cannot guarantee you that the first derivative didn't need quotient rule, didn't need product rule. To do all of these derivatives, it might be way more annoying. So we're going to need some tools to be able to do that. So I'm going to have you guys try the next one by yourselves after we kind of distinguish what it's asking for. All right, first words, find the Maclaurin polynomial. What did I just tell you? The center is 0. All right, what do you think of n equals 5? What do you think that means? This is the degree. So what is my term going to end with, my last one? That was a big question. The fifth power. So I'll have like an x to the fifth at the end. How many derivatives will you need to take? 5. All right. So you're going to take 5 derivatives. Hopefully you have your mental unit circle pulled up, because you get to plug in 0 to all of them. I would like you to try to write the 5th degree Taylor. I don't think it's going to take you that long. Try to simplify it as much as you can. I'm going to give you 5 minutes. After about 3, I'm going to put up some work. At the end of that 5 minutes, it would also be beneficial if you could have a calculator on your desk, because we're going to talk about how good this approximation is and why I care. Sin. Oh. What?
You did roll for this. The rate of that.
Oh, yeah. Nothing more than the same going through.
Really, the cost negative.
Yeah.
Oh, we did last night.
Yeah.
Derivative of negative 6, negative cost.
Keep plugging. That's okay. So you're just gonna not have a
Cosine. Dude, math analysis, this kid's the constant sin the whole time. Unironically, I was so bold. Negative.
What's up? Yeah, because you're going only to the 5th degree, so you don't need any more.
Oh. It's just 0 for sine. It doesn't, I don't like it. Just revealing some bias here.
No, we got you more than one.
0 plus 0.
I love you.
Sine is 0 is 0. Zero is 0. There's 0. Sine is y. So 0. Sine is 90
Oh my
y. 80 is 0.
Not that 8.
I'm 270.
Oh, PM.
Yeah,
I was figuring. I was like, okay, check out how they woke up. Yeah, I thought you woke up on that 5. And then
All right, if you have all the derivatives, I want you to start trying to write the Taylor series. So you should not be chilling, talking until you have a Taylor.
Why are you so angry? You put 2 as he is not Asian and all the Asians. Typical Asians of Korea.
Wait, this time, did you want us to write out?
Yes, I want you to write me the Taylor polynomial. So try to answer.
Only 1 minute left.
Oh, what the hell?
No, I got it. I got the power.
I don't know where 0 is. But you can circle it, so
0 is right here. There's all kinds of 0 here.
If you had to
Oh,
predict the next term.
This is 90. I guess this is 0.
which, yeah, and then if you flip your fingers like
Oh,
this,
you go to the
you
right.
get the spots.
Cosine of 0.
Oh, you go to the right.
Cosine 0. So the sine is
No.
0.
All right. Zero.
The sign is 0. Yeah. How is the sign of 0?
It's
It's
not.
not. It's not. We've been saying it's 0.
It's 0. I know. We're saying that.
I love when we argue the same things at each other.
Look at my thing.
Nazi.
Focus, your brother's 0, 1. You can't figure around the sign. Negative cosine is negative 1. I'm a good calculator. You should know this is algebra.
Depends on if you did true trigger.
Oh, yeah.
Did you major in mathematics?
Bracelet. My Algebra 1 student made it for me. She's adorable. That's okay. I'm very proud of it.
Really cool.
What does it say?
It says Pi Day, and it has 3 point, and she did a bunch of digits.
Happy late night.
Isn't it really nice? Kayla! Thank you, ma'am. I'll highlight it. You probably won't have like nearly anything to do, so thank you. All right, let's talk through some trig. What sign is 0? 0. Thank you, Sean, for listening. All right, what's cosine of 0? What's sine of 0? What's negative cosine of 0? Next one. Next one. Thrilling. All right. So let's write our Taylor polynomial. Now, in general, with our polynomials, we don't really want to write terms that are 0 because they don't change anything. So I could write the first term is 0, but I'm not going to. So I'll write the ones that we didn't write down here. If you wrote them, you may just want to write a second line with all the ones that are 0 not there. All right, what's going to be the actual first term of my Taylor polynomial? 1 with n x on it, right? So we'll have 0 as our constant, and then we have 1, and it could be x minus 0, but I'm going to just not write the minus 0. So I have 1x. All right, would I have an x squared term? No, it would look like 0 over 2 factorial times x squared, but I'm not going to write it because that term is 0. What would the next actual term look like? Good, negative 1 over 3 factorial x cubed. Would I have an x to the 4th term? No, it would have looked like 0 over 4 factorial x to the 4th, but we don't have it. What would our actual next term be? All right, and is that positive or negative? All right, now, talking about patterns, sine of x is going to eventually be one of the Taylor series that we memorize. But there's some patterns to it. Do you think there would be a 6th degree term? No. Do you think there would be a 10th degree term? No. There's probably not going to be any even ones. What do you think the next term that I would write down would be? Oh, I like the minus. I agree. It would be minus 1 over 7 factorial x to the 7th. Fun extension question. What do you think the one for cosine would look like? Explain. Yeah, even numbers, but it still would alternate and do all those fun things. All right, so let's get an idea of how good this guy is. So I'm going to graph it for you just so we can see a picture. Kind of watch as it goes so you can see. I'm graphing on Desmos just because it's much easier to graph than the other ones. So there's our 1st degree term. We're centered around 0, so that's that origin point. 1 over 3 factorial x cubed. We get pretty good. And then plus 1 over 5 factorial x to the 5th. So we get even better. And as we keep going, we want to figure out kind of how good our approximation can get. So let's talk about numerically how good our approximation can get. So we're going to plug in some things. Now, my second block got really confused with my directions. So I'm going to do the first column with you guys, and then I'm going to ask you to do the second column. Essentially, what we're going to do is we're going to plug in a number to both our actual function, since we can do sine in our calculator, and to our polynomial. So I'm going to show you how I would do that in the calculator. If you just want to watch and then write down the decimals, that's completely fine. Or if you want to follow along, that's cool too. So I'm going to plug in 1.4 to both the Taylor polynomial that we just made and to the function sine. So let's do sine of 1.4. Thrilling. They're behind Emory and Matt. All right, so this is the actual value of sine of 1.4. Then I'm going to plug into the Taylor polynomial. This is a little bit more annoying. So 1.4 minus 1 divided by, I'm going to do 3 factorial is 6. 1.4 cubed. Oh, goodness gracious. I hate the TI calculators. Desmos always. Anyone know what 5 factorial is off the top of their head? All right, if you don't know, 5 times 4 times 3, it is 120 times 2. And then we're going to do 1.42 the fifth. All right, did I do a relatively good job? I think so. So it's not perfect, but let's see how close. So if you want to see how close, I can scroll up, press enter, subtract, scroll up 2 times, press enter, and we're within 0.002. Now, I would argue for the amount of math that we did, that's a pretty darn good degree of accuracy. You guys got that question done in 5 minutes, and I just taught you what a Taylor series is. If you think about using a Taylor series to approximate and maybe using a computer to make that approximation, your computer's not having to do a whole lot of work to make a really good approximation, which is pretty darn cool. So I'm going to ask you to do the same thing, but plugging in 2.1. So a piece of 5 would be me plugging into the polynomial. So that was actually the second number I got. I'm just going to write out all the decimal places to really just make a point here of what we're trying to do. So we're kind of trying to make a point of how close these are versus what the actual number is. 0.985. This was, again, me plugging into the actual number sign of 1.4. And then the difference between them was 0.002, slightly north of that. So again, not too bad of an approximation. So what I want you to try to do in about the next 5 minutes is to try to figure out for 2.1 and then maybe to answer the questions below. Think about, is this one going to be better or worse? So is 1.4 going to be better as far as error goes? Am I going to be closer, farther away? 2.1 closer, farther away? And then if I even think about 2.7. So I'm going to let you plug in a little bit, give you a couple of minutes. I'm going to give you 3 to think about it, and I'm going to start writing my decimals up after 3. So try to plug those in, see if the error is better or worse. Contemplate. Think about where we wrote our. It's kind of hidden, so usually if I don't remember what a factorial is, I just use parentheses in my denominator and do 7 times 6 times 5 times 4. Okay.
Does plug in?
No.
Oh, I did the whole thing.
Yeah.
Yeah. So 1x minus 1 over 2.1.
It's kind of hidden. I think it's in what's math.
You tried to do this 3 times 2 times.
Yeah.
Do alpha, window.
Where is it? Math. And you have to go over to prob, and it's number 4. There might be another shortcut for it. I find it easier to just multiply the numbers than find it because I'm lazy.
I think I must have those brackets somewhere.
All right, you should be getting similar numbers, hopefully.
0.336.
Are we getting a break?
We can get a break after this page.
Break?
I'm literally dead.
Did give you the first 25 minutes.
I
Well,
know.
you said you were pushing towards 30 last month, so I guess this is the 30.
I did. I pushed from 20 to 25.
So this is we're completing the 30.
I don't lie very often.
We're completing the 30.
And when I lie, I generally either mean to for learning purposes or don't mean to. And I made a mistake.
You know that what?
Like when I lie to Charlotte every time I say I'm going to post an answer key and forget.
You know what I'm talking about?
All right, so you should be getting similar numbers to these. As I write them down, was the error for 2.1 better or was it worse? Was it a smaller error or a bigger? It was larger error, so it was worse. Does anyone know why? Yes. All right, did everyone hear what Charlotte said? All right, she said, because we're farther away from the center. Where did we center this polynomial? 0. It was a Maclaurin polynomial, right? What am I writing down right now? 175. So this center was at 0, just like when we write a tangent line, because it technically is a Taylor polynomial. The farther away we get from the x value we plugged in to write that tangent line, usually the worse my approximation is. So since I wrote this at 0, 1.4 is closer to 0 than 2.1 is. So usually the function could have weird behavior, but usually the farther I get away, the worse my approximation is going to be, in that the error will be larger. All right, so the error was larger. So what would you predict would happen if I moved to the sign of 2.7 and I use the same polynomial? Do you expect it would be better, worse, about the same? Yeah, this would probably be even worse. So we have to decide what degree of accuracy we're comfortable with. And one of the hardest sections we do, probably of this entire year, has to do with if we approximate what could the error be. Yeah, nothing. I would love to. So I'm going to give you guys a short break. We're not going to do a notes check today, so I'm probably just going to do the next page really quick as a kind of end to class. Yeah. For next class? No. So probably not explicitly like this. We'd have what? Probably not like that. No. So we're just trying to figure it out. All right, take a break. We'll come back and we'll do the last page to finish up class.
It's a generous 4.
Or sorry, this page. We'll save the last one for later. I like that I mentioned break and people just left immediately. That's fine.
Starbucks is planning to pay that. That was news,
The task is ready now.
Don't say it's people log in.
I knew that cat part.
You see, it's starting to come.
Is Nina still there? Nina. Oh, she left. I just want to take attendance.
Direct storage.
I want to get a 4.0. There's still no. Too terrible.
Oh, that's why that happened.
That's so sad.
Yeah, we're gonna have to make the budget on. The Model 360 again.
Oh,
So 71 up?
No way.
It's so sick. It's just like a Model Y.
I'm gonna not do it.
You want your hands checked?
We feel actually want. I mean, sometimes you better wash your hands. You look at Chick-fil-A.
I mean, sometimes.
We're saying my pleasure.
At best, I do it.
Oh, yeah. You know, we're saying my pleasure to the sink.
My pleasure.
Okay, someone else in the stall. They didn't log in.
No, I hate
I'm
that.
sorry. And then she just walked away with that.
I hate that. It's like the worst feeling on both sides of that situation. Oh.
No, she like slammed the door. I was so sorry.
All right. So I want to roll through just the next page. It probably even won't take the whole time for the rest of class, but if you're kind of thinking about Taylor polynomials in the context of BC, AB, calculus, test next time. If you're kind of thinking about this in the context of calculus in general, because Taylor polynomials have information about all of the derivatives, I can connect this material to pretty much everything we've done this year so far, minus maybe limits. So this can be a really cool way to use a calculus word, integrate other content into what we're doing right now. So we're going to play a little bit with coefficients and just answer these three questions. A and B at the bottom are connected, so we're going to do this top one and then that one. So we've got this polynomial right here, a plus bx plus cx squared. It's a second degree Taylor about x equals 0. So what else could you call x equals 0? The center. Why? What? Maclaurin. So I can call it, so it's kind of a rectangle square situation. All Maclaurin series are Taylor series. Not all Taylor series are Maclaurin series. How could I know from the formula itself that the center is 0? Anyone pick up on that? How can you tell from just the thing I highlighted in yellow, so just the Taylor polynomial itself, that the center is 0? I actually didn't have to tell you. All right, I could plug in zeros, yeah.
It said it in the video.
Okay. Emery? That's fair. All right, I'm asking too vague of a question. It's my question's fault. Remember how we saw the x minus the center? Do you see that in this question? All right, so if I just see those x's, I also know the center is 0 there. I think you guys are starting to actually try to answer the question. No worries. All right, I'm pretty sure everyone's trying to help us out with the first part. So let's talk about A, B, and C. So I'm asking you to find, with the graph of f and this random polynomial, what the signs of A, B, and C are. What do you think A represents? Actually, yes. Very, very, very lovely. All right, so this is going to be the y value of our function because that should be f of 0. So our intercept is going to be our A. Can you tell me the sign of that thing? based on the graph? Positive. We're above the x-axis. So this is the y value. All right, what usually goes in front of our x to the first term? What's b? Our first derivative at 0, so f prime of 0. Yeah, what does the derivative mean on a graph? Slope. Thoughts on the slope at that dot? Positive. I don't have any scale, so I don't know what it is, but they just want to know positive or negative. So this is our positive slope. Wow, lots of laughing happening. Lots of weird laughs happening.
Did you guys see the paper channel? I helped Miss Shuddy. So Miss Shuddy did that with her class. It's 2,000 digits of pi that are color coded.
I helped her hang it up yesterday.
Very.
Would you like to? Sure. I can try to make one. No, I can try to make one as a review for this. All right. C. How do I normally get the thing in front of the second degree term? Is it just the second derivative? Divided by 2 factorial. Now that's not going to change the sign, but I'm going to just record it because it will help in the second question we're about to do. What does the second derivative normally tell me on a graph? Concave up, concave down. What are your thoughts on this graph? Concave down. So what sign does this have? So notice I can connect material that we did even as early as back in like AB calculus to a Taylor polynomial. Also, just FYI, throwing this out here, you have 6 for your responses on the AP test. Almost guaranteed Taylor series is one of them. All right, let's talk about this guy. We got a 3rd degree Taylor. Can you see without even reading the question where it's centered? 4. I see lots of x minus 4s. 3rd degree because we end in cubed. All right, let's see if we can find f of 4. Anyone feeling bold? 2. Nice, Sam. We got our constant term from the front. Anyone feeling bolder? Thoughts on f prime of 4? I fooled you. Ooh, someone said 0. Why 0? What does the first degree, or sorry, the first derivative normally go in front of? Does it normally go in front of something squared? No, it normally goes in front of our linear term. We don't have one. Probably means we multiply by 0. So here, no linear term. I know, really tricky, right? So there's no one that's just like x minus 4 to the first power. All right. Now, -5. That's not just the second derivative, right? How did we get -5? I divided by 2 factorial. So what actually is f double prime of 4? Times 2 factorial. So -5 times 2, -10. All right. 8 also, not just f triple prime at 4. It's f triple prime over 3 factorial. Use your noggins. What is f triple prime of 4? Think before you shout a number. Want to see. What is 3 factorial? 6 times 8 is? All right, let's take one more moment to connect back to something that you all probably forgot about. Does f have a local min, a local max, or neither at x equals 4? Those are words I remember. All right, let's imagine we have a function, and I want to know if it has a local min, a local max. What's the first thing I'm going to do? I'm going to take a derivative. I'm going to set it equal to what?
0.
0. So because I'm trying to find if it's at a what? That's a very big question. Critical number. Nice. All right. So is our first derivative 0 at the place we're asked about at x equals 4? Yeah. We found that from the question previous. So yes, because f prime of 4 equals 0. Crushed it. Now, do I have enough information to make a sign chart? Well, I would argue no, because we only have these 4 pieces of information about f. We could do a sign chart with the polynomial, but that's not really legal. We don't know if the polynomial is doing the same stuff that f is. We do, however, have information about the second derivative. Does anyone remember the second derivative test? Yeah, maybe. All right, let's lead ourselves through it. Our second derivative, we got what value for that from part A? -10. Why do you think I care about that number? It's negative. What does a negative second derivative normally tell me? All right. If I'm at the flat slope point, that critical value, I have a local max. Wow. A wild M max. They did a gallery walk with trig. It looked really nasty, actually. And f double prime of 4 is less than 0. So we're going to save the rest of these, the back page of these notes for later. I would like to kind of just give you just a very short preview of what this unit looks like. So I'm actually going to go back to my last year's notes that I taught Hamza. All right. So Taylor polynomial is great. That's what we did today. We'll keep going with that. Interval of convergence is where the ratio test is going to come back. That's going to be to find essentially a domain of what's called a power series, but we're going to use ratio test for that. Both the Taylor series and power series are going to be sections where we're trying to construct a Taylor series without having to take just a million derivatives. And then the last thing we do, and this is probably the weirdest thing we do all year, is called Lagrange error bound. Lagrange is a French mathematician, but this gives me a bound for how far off I could possibly be by stopping my approximation somewhere. Now you'll notice this section in my notes used to be called, what the heck do all of those letters mean? Because there's a lot happening here. So we'll break it down. It'll be fun, but that's kind of the preview. We're going to have to wait on that preview, though, because what's happening next class? A test. As you study, highly, highly, highly recommend. You need to do 2 things. 1, make sure you know what tests to use when. What you want to avoid is having to redo an entire question when you're doing round 2. I don't want to have to use a 3rd color highlighter to tell you to start over. Also, make sure you know your conclusions. It's going to be really frustrating if you can't remember greater than 1 or less than 1, diverge, converge, all of that stuff. If you can have those 2 pieces done, then the rest is usually just an easy limit or something that's not too terrible, minus maybe integral test. You have a test review in here. There were a couple of weird mistakes. Thank you, Victoria, for helping me find those. If you find any other mistakes or want any other resources, just let me know. I am more than happy to help. What? In the answer key, there were just a couple of like really stupid mistakes that you probably glossed over or just were like, that was silly. So I fixed those now and reposted. Everything should be good to go. But if you find anything, let me know. Otherwise, we'll just test next class and then we'll continue our way on with Taylor series. Thank you for your hard work today. I will see you next time for the test on the test. Stop recording. Oh, that's right. You're not going to be here. Okay.